Hello, this is Team MB7's design video for ECE 4960. For our project, we were tasked to design and build a magnetic bearing that would float essentially frictionless under a steel plate. Some requirements for the project mandated that our system must be able to transition between a float and locked mode, that the user should be able to vary the distance between the system and the plate, that the system be controllable with a wireless remote during operation, that the onboard power supply achieve a minimum runtime of 15 minutes, and that the design be user-friendly and safe to operate. In order to accomplish those requirements, we determined that the three most important factors to our design would be that the system must weigh less than 1 kilogram to achieve any type of viable stability, the current supplied to the magnet should be ramped up or down to protect the user, system, and steel plate from damage, and that closed-loop control was required for stability in this situation. The way the system operates is by using IR proximity sensors to detect the distance the system is from the steel plate. When the IR sensor has total reflection, it outputs 0 volts, and when there is 0 reflection, it outputs 3.3 volts. It should be noted that the relationship between the output voltage and detected height is nonlinear. The TIVA then uses the signal from the sensors to perform calculations to determine the correct voltage that needs to be output to the voltage-controlled current source. This current source, as can be seen in the circuit diagram, is what actuates the magnets. This is the system in float mode. It initially maintains a 1 mm air gap between itself and the steel plate until prompted by the user to do otherwise. As you can see, the system essentially floats frictionless under the steel plate. In this video, you can see the user changing between the locked and float modes using the IR remote. Now let's take a closer look. As you can see, when the button is pushed, the system gradually transitions between the two modes. As mentioned earlier, this is in order to protect the system and the plate from undue damage. This gradual transition also promotes stability by reducing any sudden jolts that could be experienced otherwise. The user can also use the IR remote to vary the height of the system. In this example, the system is first moved down 4 increments and then back up 4 increments. The maximum distance away from the plate the system can safely be is 2 millimeters. Getting a closer look, you can easily see the height vary. In this example, the system is moved up and down 3 increments. Once again, the gradual transition promotes stability within the system. A unique design feature that was added to our system was one magnet lock mode. As the name suggests, any of the 3 magnets can be locked individually to create a pivot point around the magnet. While the term locked is used, essentially the current through the specified magnet is higher than the other two, but not high enough to physically lock the magnet to the plate. Otherwise, the system would not be able to pivot and would potentially damage the plate. In conclusion, we were able to successfully accomplish all the design requirements and add further design features to the project. With the 5-cell lithium polymer battery that powered our project, we were able to achieve 5 hours and 45 minutes of runtime in float mode, which was significantly greater than the 15-minute minimum.